All right. So let's keep going. So we took a break for about 30 minutes. Come back to everybody on Zoom, and we'll come back to everybody here. So let's just recap of sort of where we are. So what's happening so far. So we set out to talk about 7 common narratives, right? Fairness. So far we've covered 4 of them. We've talked about fairness issues only coming up when working on people or people-related recognition. Once you define the metric, algorithmic fairness is straightforward. Bias in data sets is inevitable. You need to learn to live with it. Oh, awesome. Thank you. And problems of data set bias are getting better or worse. Sorry, this seems really loud. All right, is it really loud or is it good? Okay, it's good. Okay, great. Okay, so we've got 3 more narratives to go through, and then we'll kind of open up the floor for discussion. So I think the next one that we are diving in is the claim that, or the narrative. It's not a claim, it's a narrative that we want to discuss. Is the problem can be solved at the feature level. So the tempting narrative here, right, is perhaps we can isolate the fairness problem, for example, via representation learning. So rather than kind of thinking about the bias in data sets or sort of solving it from that perspective, we can just say, okay, the data set is what it is, but let's do representation learning. So let's learn a representation that does not contain social biases from this biased data set, such that then any models or classifiers or whatever we do that we build on top of this representation will not be biased. And actually, so this tutorial was inspired by this excellent tutorial on representation learning and fairness that was done by Mustafa and our very own Sammy here. So I made the slide, so I'm allowed to call this excellent. He didn't call his own tutorial excellent, but it's very good. It dives into sort of the different representation learning approaches to fairness. This was a few years ago. There's a video recording, there's slides online, so if you're interested, definitely sort of go into this. I'll borrow a couple of slides from there, but by and large, they do the best kind of overview of the literature on this. So loosely speaking, right, representation learning is the task of estimating concise and informative data summary. So you're given some data set, perhaps some labels, and you're trying to summarize it down into a representation that then you could be using for whatever kind of downstream tasks you have. So what are the pros of incorporating? They talk about pros and cons. I'm just going to talk about the pros here, right? So why would you want to incorporate fairness using representation learning? So it can be more efficient, especially with reuse, right? So you could do this once on a data set, and then whatever tasks you're sort of going to build from this data set, you use the same representation. You don't have to worry about fairness. It can be employed when the user, so the user is in somebody who is going to take this representation and then do things with it, then sort of train whatever they want on it. When that user is either untrusted or just apathetic, they just don't want to deal with these fairness questions. They feel it's sort of out of their scope of expertise, and so you can give them, they're relieved of the burden of directly reasoning about fairness because you give them this representation and say, okay, now do what you want with it. This also inherits other good properties of representation learning, right? So interpretability in some cases, transportability across data sets or institutions, perhaps some robustness properties, perhaps some privacy properties. And also, so audits, trying to ensure that this system that you're building is fair. So these audits can be much more efficient, especially when just you're auditing the representation, right, rather than the more complex system. And so again, what we're trying to do here, right, is to take our data and then compress it into some featureized summary. So why is this challenging to do in a way that's fair? And so for the purposes of this section, so fair, so let's just say that supposing your data had some attributes for, so supposing that this is tabular data, let's forget about computer vision data for a second. So suppose this is tabular data, you have a bunch of features that sort of describe something. That the canonical example is somebody who might be applying for a loan, and you're trying to figure out whether to give them a loan or not. And suppose within this data, there is a feature that corresponds to, let's say, gender, corresponds to the person's race. And so you say, well, okay, maybe the representation learning of this is okay, I'm just going to remove that feature, and then the remaining features, that's my sort of fair representation, and now there's no concerns. So the key challenge, and this is the key challenge in fairness in general, but particularly when you're doing representation learning, is the idea of redundant encodings. And so here's how to think about this. So this is a paper from KDD 2008 that has this like really nice figure articulating the problem of redundant encoding. So suppose you have a data with some discriminatory items. So a data set of people where let's say again, applying for loans, and in describing the person applying for the loan, you have information on their gender or their race, right? So now when you learn a decision rule about, let's say, whether to give somebody a loan or not, you can see that, okay, maybe this rule explicitly takes into account their gender or their race. And so then when you look at these decision rules, you could check directly for whether it is discriminatory according to legal laws or legal definitions about what you can and can't use for making this prediction. And then you can identify these discriminatory rules, right? So if A here is a protected attribute or value of a protected attribute, right? So making a rule based on features A and B is problematic. However, what happens when you have a data set without discriminatory items, right? So you've removed gender and race from the data set, you're learning decision rules. So if you have some background knowledge to try to understand sort of what are these different features that exist in the data set, you might be able to check for indirect discrimination through an inference model. So what does this mean? So for example, if you have a feature like zip code in your data that's in theory does not have any discriminatory items. If you have something like zip code is very much a proxy for race, at least in the US. So just because the data set seemingly does not have discriminatory items, when you have these sort of background information about the correlation between zip code and race, right, in practice, even though these decision rules might appear reasonable, they may in fact still be discriminatory because of these correlations. So you can learn this based on these as background information. You can check indirect discrimination through an inference model. And so what this means in the context of representation learning is that if you're trying to remove all information that can lead to bias, right, you're trying to not just remove sort of particular feature, but you really have to be very, very thoughtful about how much information do you remove such that there is no danger of any kind of harm or discrimination being learned downstream. And so the way that this kind of manifests itself frequently in representation learning. So this is a paper, for example, from ICML of 2018. So this is representation learning. There's an adversary criticizing potentially unfair solutions. So you have your data X, it's run through an encoder to produce a latent representation Z. There is then a classifier that can be trained on Z to predict your target labels. And there's some adversary that takes in this latent representation and basically tries to infer the protected attribute, and you're trying to train this representation in a way that the adversary is making sure that the latent representation, the Z, does not contain any sensitive information. There's lots of work of doing this, and again, the NeurIPS tutorial covers this in much more depth. So it doesn't have to be done with an adversary. It can be done by trying to learn representative prototypes without an explicit adversary in a way that sort of are more fair for various definitions of fairness, such that again you can then build models on top of these prototypes and so on. And I'll also point out there's also connections here, right, to privacy. So you might be trying to learn this representation in a way that's both doesn't contain biases, but also potentially like doesn't contain sensitive information about people, such as you can't de-anonymize somebody based on the information that's contained in the representation. So there's connections there. And so within computer vision, right, this has been applied to try to debias from a bias data set to build a de-biased representation. So for example, there's a paper in ECCV of 2018 that's called Explicit Removal of Biases and Variations from Deep Neural Network Embeddings. And so the core idea, right, is that there is a neural network that does some kind of primary classification task, whatever that is. And then there's sort of additional loss functions that say, I want to be able to do this primary classification task, but I want to be invariant to, I want to do this in a way that an adversary is not able to classify, for example, the gender of the person depicted in the photo from just the feature representation, so the FC7 or whatever sort of feature representation. And so they show these great T-SNE plots where the baseline network, right, if you just train it to do the primary classification task, if you show the feature representation, it sort of partitions very nicely. So the men and the, or very problematically or very nicely. So the men and the women are sort of nicely separated in this T-SNE plot. But if you create sort of a blind network, right, a network that where you add this additional confusion loss that sort of encourages the representation to not contain gender cues, then you get this very nice mixture. So now in the representation, right, you arguably remove the gender cue. So what are some of the problems or challenges with this, or sort of why does this fail? So first of all, so we have a paper in, so this is by Zi Wang in CVPR 2020, where we have this sort of, we apply this, so actually a slight variation on this previous adversarial method, which I'll talk about in a second. But we have, a baseline model, right? It's trying to predict some target labels, in this case, object classification, right? And you have some protected attributes. So when you train the baseline models, right, so it nicely separates the target labels. So the target labels here are the different colors correspond to the different classes, right? So they're kind of nicely separable and learned. But the protected attributes are also the red and blue are also kind of separated in this plot. When you train with an adversary, so again, as expected, the protected attributes become sort of confused with each other. So the adversary is doing what it's intended to do, but the target labels also become confused. So you are harming the representation to kind of a large extent, such that your accuracy on the target classification starts dropping pretty dramatically. And we run a bunch of experiments on this, and we sort of show this result is quite consistent. And there's other approaches that would allow you to do this in a much better way, using sort of what's called fairness through awareness, which is not trying to like hide the gender information or hide the protected attribute information, but actually leverage it in sort of explicitly in building the model rather than trying to ignore it. So some of the kind of challenges with adversarial debiasing, right? So we have to think about the fact that whenever there's a correlation between the target label and the protected attributes label, right? So if you're trying to classify objects, or you're trying to classify scenes, and those scenes are correlated with people of particular gender or people of particular demographic, right? So that means that if you can predict the target label perfectly, then the protected attribute will be predicted above random chance, just because of this correlation. So when you're trying to do the debiasing, first of all, you really have to be careful to make sure that this is not, you can't predict gender above random chance, but actually you could, and again, there's papers like the Swackley 21 paper that talks about kind of decorrelating and doing statistical independence rather than saying, I want to make sure that gender can never be predicted from the representation. The second issue, and so this is, I mentioned, we did a slightly different adversarial method in the previous slide. So this is the method. So here, the other kind of intricacy is optimizing the target loss may actually be inadvertently helping the adversary. This is related to the fact that the target label and the protected attribute labels may be correlated. So here, this is a paper in the AI Ethics and Society conference in 2018. So they point out that if you look at the gradient for the target loss, and then the gradient for the adversarial debiasing loss. So the adversarial debiasing loss says, I'm trying to prevent this representation from learning anything about the protected attribute. But as you're optimizing the target loss, so you're actually sort of helping the adversary. These two things are basically pointing in opposite directions from each other. So what you want to happen with the adversarial debiasing versus what you want to happen with your actually learning task, those are pointing basically in opposite directions. So they, propose a compromise where you're allowed to optimize the target loss, but only insofar as it doesn't hurt or doesn't help the adversary. So finally, when we talk about, so this is hot off the press, this is about to come out on arXiv. I was very excited to talk about this result, and of course we didn't quite put it up on arXiv yet, but it's coming up, it's been submitted, so it will show up in the next couple of days. So when we think about computer vision data sets, and we think about removing bias from computer vision data sets, in particular, so here we're looking at removing gender bias from computer vision data sets. So how difficult is it to do? How embedded are gender cues in visual data sets? So let me explain what is going on in this plot. So on the y-axis, I have the ROC AUC, so essentially the accuracy of a gender artifacts model. So a gender artifacts model is a model that's classifying if the image contains a person labeled as female or male. And again, we've talked about the issues with those labeled people. So this is the data set is on the COCO, the gender labels, again, as before, derives from image captions, and it's complicated, so they're not perfect. But we're trying to use a model to predict whether this image contains a person labeled as male or female. On the x-axis, we see different resolutions of the images. So we take the images and we scale them down from 224 by 224 all the way down to 7 by 7. And so this blue line here at the top, these are color images at different resolutions. So we take these images and we are progressively scaling them down so the accuracy of this model drops, right? So it's not able to differentiate between these two sets of images more and more and more as we get to lower resolution. This is the same thing for a grayscale model. This red line here is random chance. So already you might notice that color images, you are able to differentiate whether this image is likely to depict somebody who appears to be male versus female above random chance, even at 7 by 7 resolution, right? So 7 by 7 resolution, you can't tell basically anything about the image, but you seem to be able to tell what gender the person is likely to be. Again, with the usual caveats of, gender annotations and gender labels. And this purple line even sort of makes us point even stronger. So this is model trained on just 3 features. So this is R, G, and B, average color of the image. And just on those 3 features, we can get almost to 60% AUC, right? So much, much above random chance in doing the gender. So what does this mean? So this means that when we talk about let's train a representation from which we can't infer gender, like let's train a representation that's fair with respect to gender. Let's abstract away this problem from the downstream classifiers and just train a very robust debiased representation. So this is the challenge that you're trying to work with. I mean, how much information do you need to obscure from the image in order for it to actually not have gender cues? And the answer is likely an insurmountable amount. And there's another really cool result that just came out similarly for medical images. So this is even weirder in some ways, right? So they've analyzed, so this is a paper that was just published on May 11th of 2022 called AI Recognition of Patients, Race, and Medical Imaging, a modeling study. So I'm showing some of the medical images that they analyzed, and I'll just read you the quote sort of from the abstract of this paper. So in our study, we showed that standard AI deep learning models can be trained to predict race from medical images with high performance across multiple imaging modalities. We also showed that this detection is not due to proxies or imaging-related surrogate covariates for race, such as body mass index, disease distribution, or breast density. Finally, we provide evidence to show that the ability of AI deep learning models persists over all anatomical regions and frequency spectrums in the images, suggesting that efforts to control this behavior when it is undesirable will be challenging and demand further study. So it seems that sort of protected attributes like race or gender are very, very, very deeply embedded in visual data sets, both sort of scene data sets like COCO, but also even medical data sets. So that means that it's very, very difficult to do any kind of abstraction when we're talking about fairness of these computer vision systems and abstraction in the form of reinforcement of representation learning. And so let's discuss narrative 5, that the problem can be solved at the feature level. It's possible to do this kind of abstraction. So on the pro side, so I do want to certainly give credit, so we can make some progress. And representation learning can help mitigate bias. So typically at relatively low accuracy costs have done well. And there is, again, a lot of body of work trying to do this and making headway towards this, making steps towards this. And again, we'll refer you to the NeurIP tutorial for sort of more information on that. But the con is that visual cues are really pervasive. So removing race or gender artifacts from images appears at best extremely difficult. And so any claims about fairness being solved at the feature level also can lead to overconfidence, carelessness, and issues downstream, particularly because, right, it doesn't appear to be that this is actually feasible to do based on you know, sort of these kinds of simple analyses. However, for a conclude here, I do also want to point out, so it's not clear if these kinds of correlations or cues or artifacts in the representation are actually necessarily harmful by themselves. Right, so the issue really comes in what happens with them downstream. It really comes with what happens with these when these representations are used, but then this also kind of gives credence to the claim that we have to be thoughtful in all stages of the pipeline rather than just abstracting away at the representation learning stage and say, okay, we've learned a good representation and we're done. No, our representation is going to have issues, but if we're thoughtful about how we do things downstream, that may not be a problem. Any questions on narrative 5?
Any guesses on why gender is persisting at 7.7?
So yeah, so I think gender is persist. So the question was any guesses for why gender is persisting at 7x7? Yeah, so gender is persisting in the color cues, and it's persisting because of the same way of the fact that they people appear in different scenes, right? So it's basically the backgrounds of people are different, right? So it's basically appear in different scenes, and thus you can predict based on just like the overall scene statistics, right? Is it more green, so is it sort of a grassy field, or is it more blue, so is it you know, outside against the sky, or is it more brown, so it's sort of indoors? People also will appear, so people of two genders will appear at different sizes in the image. So women tend to be pictured more close up, and men tend to be pictured more far away. The people in COCO are predominantly lighter skin, so close up suggests a certain color, again, certain color distribution.
The same experiment was the distribution of gender even, or was it representative of like actual?
So this is ROC, so I think it's invariant to differences in frequencies. I believe we've done it, but I actually don't remember off the top of my head. I think we did both versions of this. Yeah. sorry, the question was, was the distribution of genders equal or different?
What about the medical images? That was actually even more intriguing in the sense that, you know, if it is a mostly certain race-dominated neighborhood and it has certain kinds of captured devices, and you know, you might be picking up on the medical capture device that is most commonly used in that those neighborhoods, as it were, right? It
Yeah.
might be some socioeconomic thing that you are actually picking up on or something. So I'm just wondering what it is it could be, because I had this impression that if you on the inside, I mean,
yeah, so the question is, I'll just repeat. So the question is, what about the medical images? So this is an even more compelling example. And so the question is whether this is, so I know there, the question is whether this might be because of the medical imaging device. So right, so there have been studies that sort of demonstrated, right? So a lot of the time in these data sets, it's collected across different hospitals, and then the quality of the imaging device is different in the different hospitals, and then that is correlated with income of the neighborhood that the hospital is based in, and that is correlated with race of the patients and things like that. So that can be frequently used to infer race. So I believe they actually controlled for all of that. So it's super interesting. I don't have an answer to this. I don't really do medical imagery. It's just a fascinating study that, yeah, I really don't have an answer. All right. Sorry, go ahead. Somebody on Zoom was trying to talk. Is that what's happening? Go ahead.
Yeah, I'm not sure what that was.
All right, so Sammy, I
Probably
think I'm
not,
gonna
Okay.
pass it off to you. So I'm gonna remove spotlight. I'm gonna spotlight you. Okay. I'm gonna rotate the camera. Audience, and I'll come sit there in the front row.
Okay, great. Thanks for all the hard work on your end. I get to just hang out remotely. Okay, so I'll move on. Hopefully you can hear me. Yes? Okay. So I'll move on to the next narrative, which is tied to, I think, many of the discussions we've had already about the extent to which we can just focus on the training data sets as the source of issues, and sort of solving the issue with the training data set solves our problem. So to discuss this, there's a cartoon I like to show, which many of you might have seen. It's from SKCD, which highlights maybe some early thinking on machine learning, which is just throw data into some linear algebra system, magically things work. If they don't work, move things around a bit, eventually they'll work and you'll be fine. Of course, we don't build, I'd argue that we possibly build systems like this at some point. We definitely don't build systems like this now. And some of the reasons we don't is because we know that there can be lots of issues throughout the pipeline in constructing algorithmic systems that are beyond just trying to get good results on a training data set. So in particular, when we see failures of fairness or any other issues, but here focusing on fairness, what can we blame, particularly if it's a failure in deployment? Of course, this is a complex question, but I'll highlight some of the issues. We've mentioned some of these before. Some obvious ones are confounds, which can mislead the algorithms or mislead the predictions. I think in particular, and maybe reasonably pernicious, so sort of shows up a lot, is that there's distribution shift between train and test very often. And it's not clear the extent to which fairness guarantees that you might be able to produce on a training data set transfer to fairness guarantees at deployment. There are also feedback loops in many the implementations of algorithmic systems, again, this changed the distribution from what you're training on, because now you're getting data from results driven by the model that you built in the first place. And this can change the nature of the distribution to where guarantees that you thought you had from training no longer hold. I mentioned briefly, but I'll mention again, there are also lots of challenging questions about how we pick the right variables, proxies, and what those mean when we build machine learning models, the reductionism that needs to happen to actually build any sort of feasible, practical, useful system. And we talked a little bit about measurements. So again, different measures can behave very differently. Society changes and context and stakeholders could possibly change. And so a system that seems perfectly reasonable at some point over time, as the rest of the framework changes, can actually then look much worse in retrospect. So clearly, sort of the change of time and the nature of the change of distributions makes looking only at the training data set incomplete in terms of trying to narrow down notions of fairness. Here's a table I showed earlier showing cartoon of algorithmic development lifecycle. And as mentioned, many of these questions of generalization, data set distribution shift, feedback loops, and all that show up in post-deployment, and trying to mitigate or find tools that allow us to do continuous evaluation to make sure that we don't miss something that shows up later. And so maybe, I guess, as an argument, it's not enough to think just of the data collection as the full source, because again, issues can come up everywhere. And maybe the data is not the full explanation. Using the same exact figure, you could also argue the opposite. So the argument there would be that the data is not representative. And so because of this, it's not capturing the distribution shift. And this is why the failures are happening. So again, maybe not definitive in terms of an answer, but allows for multiple arguments for the question of training data sets being the source of fairness issues. Another, I think, interesting view on this problem of differences, training data sets being the source of error issues, is looking at how we measure. So I talked about metrics earlier. What do the metrics actually capture when we think of metrics in at least the most common versions of metrics for evaluating fairness? And so I'm highlighting here the observational group and individual fairness. And what you might notice is, while you could measure anything about the, say, training data or the original task, most of these metrics focus on error behaviors across groups, which means not just the data differences across different groups, but actually how good was the model in making predictions across different groups. Again, I think this makes it challenging to blame fully the data, because the model clearly has a role. Now, again, the counter to that argument is that the differences in prediction maybe are driven by data. But the main point of this slide is to highlight that there are, at least most of the ways we think about fairness metrics actually boil down to model prediction error differences, as opposed to directly about the data. So the data components are at best indirect. Specifically on the question of generalization of fairness, there's a recent paper that I was a part of, and I think I'd encourage you to take a look at, which asks the question of generalization of fairness metrics. So do we expect that if I train a model with, say, demographic parity guarantees, that it will actually achieve demographic parity when, say, applied on a slightly different data set? Depending on where you stand, this may be obviously yes or obviously no. I'll say in this example, we have a couple of results on medical domains that show that generalization often breaks. So models that seem to have good behavior and source in terms of performance and fairness, because they're trained in this way, for instance, will often have very disparate behavior depending on the nature of the shift between the source and the target, sometimes even when the prediction performance is still reasonable. And so just like any other statistical quantity, many fairness metrics, being statistical, also have dependence on the nature of distribution shifts, and those can affect significantly the fairness guarantees that you can give. There's other work thinking about fairness in machine learning beyond the sort of training phase. So I like this work, and I think this also pushed forward a whole agenda of people thinking about constructing models and then embedding those models in real systems. And so what this paper tries to do is have a very simple sort of feedback loop system where you construct the model, it's deployed, and then you have sort of long-term indicators of what happens to different groups when this model is deployed in some real system. And so some of what they show is, I think, maybe most striking, that sometimes trying to enforce common fairness criteria may not improve behavior over time. So standard things like, say, demographic parity may actually lead to worse behavior over time, and in fact may cause harm compared to cases where you did nothing. So there are actually cases where the standard phrase of doing something is better than doing nothing may actually not hold. You may actually make the problem worse by intervening. And they show this with, I think, some very compelling examples worth taking a look at. So to expand on this narrative, or to discuss this narrative, so very commonly we think of fairness issues as training data issues. And this is often expanded to include both biases in data collection, distribution shift questions, feedback loop questions, but also human biases that the data itself encodes, and so the models will encode. And as mentioned, many real issues in deploying systems make this problem worse. However, as I've hopefully argued, all of the steps in the development and deployment pipeline can create additional issues. And in particular, maybe importantly tied to what Olga was mentioning earlier about representation learning, guarantees given at a certain step of the process don't imply guarantees in subsequent steps. It's actually quite easy to undo guarantees from any step in the training pipeline, say a representation learning step, with the next, say, final predictive learning step in the following. If you follow a predictive learning step after a representation learning step, it's quite easy to undo, say, fairness guarantees that you might have given. And there's some work that tries to dive into this question and tries to understand cases where you can give guarantees, which I encourage you take a look at. It's called fairness under composition. So I think my current view anyway, and maybe some food for thought, is that while we generally like to use training data sets as a convenient villain for most fairness issues, I think that view is often incomplete. And very often there are many other ways that we can have issues creep in. And so we really do need to think about the whole system if our goals are to improve fairness properties of many of our models. Okay, so I can answer if there are any questions briefly before going on to the next one. Okay. Oh, there is, okay. You're muted, okay.
Sorry about that. Sorry, that was a. Can you hear now, Sammy?
I can.
All good?
Yes.
Okay, perfect. Sorry about that.
Sure. I guess I was just, I wanted to ask a question about the kind of last point you made about the data set you can fill in. I guess a thought I've had about some things I've seen is essentially like, I guess to be a bit controversial, is like, why are you even asking this question? Or what is the problem you're trying to solve the actual culprit? I guess in terms of like, let's say classification of face images or something like that. Maybe that is the upstream explanation. Do you have any thoughts on that comment?
I apologize. I missed all of that. I didn't pick it up. Olga, would you mind maybe summarizing?
Can you hear me clearly, or?
Not that clearly. It's a little bit difficult, and I missed most of what you said.
Ask from this microphone, because I think this microphone is the better microphone.
Is this clearer?
It is. Sorry for the awkward positioning. Yes, this is clear.
Sure. I guess I'll briefly. Your last point about the data set being a convenient villain. Is it, I guess, possible that maybe it's even more upstream, kind of referring to the machine learning problem you're trying to solve? Like maybe the question you're asking itself is not something that can be answered without being biased, regardless of if your data set is perfect or your model is fair.
Yes, I think that is often true. So that's a great question. I think there are questions, we'll touch on this a little bit at the end, but of course there are many questions that I think are tricky or problematic, and maybe we should be using machine learning for. I think, I guess beyond the questions, I guess the pro part, I maybe should add, there is a part of the set of problems, assuming the problem is well specified and reasonable and all that. I think there are reasonable arguments for why better data would remove some of the, at least the most visible issues, say bias sampling across groups and things like that, that can make a good difference. But I think you're right. Everywhere in the pipeline, I think it can be easy to have bad decisions creep in that break the properties that we'd like of systems we're building.
Thank you.
Come up to the podium.
Yes.
Right, I think no takers at the moment.
Okay. Yeah, it's intimidating doing podium questions.
Yeah, sorry, folks.
Maybe not.
We're doing our best here.
Okay. So thanks for the discussion. We're gonna move forward to narrative 7. So narrative 7 is meant to be maybe a slightly tongue-in-cheek, but thinking about the frameworks that exist and the extent to which they're complete solutions, which you'll sometimes, though rarely, hear from particularly proponents of various frameworks for fairness in general. So so far we've discussed. Okay, so I think some of the biggest challenges in thinking about frameworks is the fact that in real systems, different stakeholders have different notions of what they care about and what they think fairness might mean. And I think this is coalesced in the community thinking about fairness as a socio-technical problem. Similar in many ways to things like privacy and security, in that they involve both technical solutions, but also the social context. And I think that this is okay. And I guess I'll argue or maybe state that it probably is useful as a field to get more comfortable with this being the status quo of solving fairness questions. And maybe to expand on this, the way some of this exhibits is that there's tension between different stakeholders and what they want from, say, fair machine learning or fair algorithmic system. So individuals typically will worry about bad outcomes, say counterfactual outcomes for, say, someone that they consider similar. Policymakers often care about population behavior. So they want to know, on average over my population, am I doing worse or better for a certain segment of the population? And so they will typically, often will focus on population measures. I think within the field, we also tend to gravitate towards population measures because that's what machine learning tools and statistical learning tools are good at. They're good at giving you population average guarantees, maybe much less good at giving any kind of guarantee that is individual without averaging in some sense. Lawmakers and advocates often focus on the harms that you might end up suffering and equity, but we'll try to argue this through individual cases. So it's some mix of individual and population. And media will often focus on individual cases, and I think arguable whether these cases are representative or outliers and what we should do when we have those differences. And so, as mentioned, to the extent that we use statistical systems, the kinds of guarantees we typically can give are averaging style guarantees. And trying to make strong guarantees about individual cases, I think, is quite a bit harder. And it's not clear that they're really good tools yet to do that in general. And if one thinks about this from the point of view of the stakeholders, I think it's still unclear how to build models, how to build strategies that can satisfy, if you wanted to say, all of these stakeholders simultaneously. I think of this as still maybe an open question. Thinking from the point of view of frameworks, I'm just flashing up the slide where I covered the various frameworks that are common as ways of thinking about fairness. Digging a little bit, there are lots of pros and cons to different ways of considering fairness. So individual fairness, I think, has the advantage of potentially being intuitive to explain because it's you can explain it in terms of an example because it's individual. And it has some nice statistical properties, maybe separate but useful, because you can connect individual fairness guarantees to notions of generalization and robustness. So that is a good property. And in special cases, you can connect individual and group fairness to each other. I think it's another useful property that is in the Fairness to Awareness paper. However, as noted, there are some significant challenges in coming up with good metrics, partially solved using elicitation, as we've already outlined. In general, individual fairness implementation tends to be quite expensive because it's about examples. So it generally scales at least quadratically because you're looking at pairs of examples or worse with the number of examples in your data set, which can be a non-starter for really truly large data sets. Again, I think it has an open set of questions there and better scalable tools for implementing individual fairness with better scalable properties. I think there are arguments about cases where we expect causality to be the driver. I'm thinking of applications in healthcare where we know that some of the differences we're observing are biological in origin. And so it's not clear if we should be enforcing similarity of outcomes if there's biological reason for the difference. So I think this at least requires some additional thoughtfulness in coming up with better ways of implementing strategies like individual fairness. Similarly, for group fairness, it tends to be relatively efficient because it deals with sort of averages across groups, which maybe might be easier to reason about. As mentioned earlier, policymakers tend to like it because it tends to be about the overall population. There's a lot more work in it. I mentioned briefly implementing it using pre-processing, in-processing, post-processing as training strategies. There's a lot more evaluation as well. So it's maybe a lot more literature to depend on. Some of its challenges include determining the statistic that you want to use. So what measure? More than that, and tied to the question earlier, you also have to decide how you measure violations, so how you measure differences between the statistics across groups, and different measures actually give you different answers. It's the same, think of this as same as for classification, if you want to maximize accuracy, you could choose different losses. Which again, logistic loss, squared loss, things like that, and you actually get different performance. And so there's, again, a gap there in terms of open questions on how to pick this. Again, partially addressed using elicitation approaches. One challenge tied a bit to privacy is that you require, in general, I'll talk about some special cases. In general, you need knowledge of group identity, either during training or during deployment, or ideally during both, which overlaps with privacy in non-ideal ways. And again, we've talked a bit about how this can be related. So observational measures and how they connect with causal measures in settings where we think causal measures have a role to play. I wanted to do a bit of a deeper dive into some of the interesting subcases, because some of this work is related to work that I've done. I'll just run through some, I guess, tools which may be useful if you're interested in looking at some of these things. So if you're interested in mitigating group unfairness, but you don't have group labels in training, then, so if you only have group labels in training, then there are a set of methods that the community has developed which look like empirical risk minimization, where you train classifiers, but essentially all of the information about sensitive attributes is only used during the training process and doesn't need to be part of the set of features at deployment. If you only have sensitive attributes at test time, then one can use variations on black box approaches, black box learning approaches, where I have a validation set where I can query how good a particular model is with respect to fairness properties, but I can't actually see in training any, say, sensitive attributes or any group identities or other kinds of label information. Yet having black box access to this fairness metric is often sufficient to still train an effective model if I only have validation or test access to sensitive attributes. And then finally, if I don't have the group labels anywhere, either training or test, then there exist techniques, things like multi-calibration, where you define large sets. Effectively, you can think about this as defining all possible groups of a certain size, as an example. So computationally defined groups, not directly tied to identity. And you can make strong statements because you know that these are supersets of groups tied to identity. So if you do well with respect to these computational defined groups, you will likely do well here measured as small differences between these groups. Then you'll likely also have small differences between sensitive attribute groups. The challenge here, again, is that because you're creating so many more groups and that you're trying to equalize over, they tend to be very conservative. And so the hit on the performance size of things can be quite large and might be much more than what you need to actually get good properties with respect to, say, a standard fairness measure. Another, I think, interesting tangent is thinking about adversarial vulnerability of algorithmic fairness. So this is separate from using adversarial tools to make your model, your, say, representation better that Ova talked about. Here, I'm thinking about training a model to satisfy a fairness measure. And I'm asking the question, can I construct adversarial approaches that will actually make my model seem like it's doing a good job, but actually systematically have errors that will then lead to unfairness at deployment? And there's a growing literature analyzing this. I think it's now, it's maybe not surprising because, again, this is a property of any statistical notion. And maybe all models, that there are always these blind spots that can lead to adversarial perturbations. I think an interesting one, tied again to some of what Olga mentioned earlier, is one that was noted by Kearns et al., where they coined the term fairness gerrymandering. So this is an interesting adversarial setting. The idea here is that I construct a classifier where across groups separately, it looks like it's doing well. So for instance, if I'm going to use age, gender, and race, so here in the figure on the right, I can construct a classifier where if I look at old versus young, it has similar behavior. Male versus female, it has similar behavior. Black versus white, it has similar behavior. But if I look at intersections, I have very big differences in those intersections. So meaning, if I look, for instance, specifically at the block A, which is old, female, black, this model does really badly compared to another sub-intersection. And the way this works is that you can play games with averages, because averages are sort of central tendency to any kind of aggregation that looks for the center. The trick you can play is essentially get the same center behavior, but put stuff farther and further apart at the tails. And so that's the trick that this adversarial method does. So you systematically do much, much worse for one group, but then do better systematically for another group. It's like that the average looks similar. And I think early on, some of this was used to argue individual versus group fairness. I think that's unnecessary, but just mentioning some of the history here. So, and maybe a simple fix to this problem which has been implemented and work that I've been involved in, is that you can simultaneously enforce fairness for multiple subgroups at the same time. Here, this is multiple subgroups known during training, so these are identified. And this can be a way to get around this averaging being a vector for this kind of adversarial behavior in the worst case. I'll mention as an aside, post this paper we've done some experimental analysis. This is not published anywhere. But our observation seems to be that this truly is adversarial behavior. So if I train a standard model, say for good false positive rate behavior across larger supersets of groups, so old, young, male, female in this case, it tends not to explicitly or systematically have this gerrymandering behavior, so do worse for subgroups. However, we know that you can construct classifiers that will do that. So switching gears a bit, talking about causal fairness. So it has some advantages. It comes with causal guarantees, which I think can be good in many applications, particularly applications where we have some knowledge that helps us to specify a causal graph, so this data generating process. And can be a really good match to scientific processes and applications that are closely tied to scientific settings where we have interventional interventions are in common use and thinking about the implications of algorithmic systems. There's also, I think, a nice line of work trying to connect observational and counterfactual fairness. And so what they argue there is that if I'm interested in counterfactual fairness, under certain graphs, this becomes equivalent to some of the standard group fairness metrics. So that's maybe a nice to have. Some challenges, causal frameworks are quite sensitive to the causal graph. I'll refer to this paper by Cobertus et al. So what can happen is that there are multiple causal graphs that give you the same observed data distribution. So I can construct a causal graph that sort of will pass any test that you use to check, is this causal graph reasonable for my data? However, the causal graph can be constructed such that it does well with respect to the measured causal fairness restriction, but is actually not meaningful with respect to sort of real world behavior. And the trick that you can play is that unmeasured confounds can actually be used to sort of manipulate causal graphs in ways that you can't tell from data. So it requires this strong faith, if you like, in the data generating process that can be broken if I don't measure parts of the world, which in general is true. I'll also say that they tend to be a bit more complex than any of the other approaches that I've outlined so far to implement and enforce. And to some extent, causal definitions require some more expert technical explanation. If here, for instance, I glossed over the definitions. Some of you might already be familiar with causality in general and causal notions, but whether or not you are, probably might agree that it tends to require a bit more technical work than, say, standard predictive or observational statistics type approaches. So to summarize narrative 7, I think there are lots of great frameworks. I've mentioned, I think, some of the most popular ones around observational and causal fairness. They can capture important aspects of the fairness problem, but by definition or by construction are focusing on certain aspects and ignoring others, and so might have blind spots. Maybe as a con, as mentioned, fairness is complex and social technical. Different stakeholders have different things they want from the fairness system, and frameworks might tend to oversimplify some of the complex issues. I'll mention here, I think one of the goals that we wanted to state for this tutorial, our goal here is not to, I think we want to be clear to say that we think advancing the algorithmic contributions are important in their own right. However, they may not actually be addressing, or it's not a direct case of addressing fairness issues unless it's connected to the social technical issues that underlie fairness, as Olga mentioned. However, these can still be very useful and good things to do. So I think there are lots of interesting open questions down this road. Thinking about maybe new frameworks that can capture more complexity around the full pipeline of building fair algorithmic systems. The extent to which we can maybe, before coming up with new frameworks, can we combine existing frameworks, because sometimes they capture different aspects of what we think are good about algorithmic systems. So can we capture, say, some other properties individual fairness has combined with, say, group fairness, so we can both satisfy, say, policymakers and individuals? Can we capture some of the properties that causal fairness has? Does doing this actually help you maybe mitigate some of the worst shortcomings of each of these frameworks? I think that's a interesting open question for the field. Okay, so with that, I'm done with all of our frameworks. I'll leave open questions on narrative 7 before we switch to a summary of the overall tutorial. And if you're feeling brave, you can come out to the podium.
Great, volunteer walk you through like.
Yeah. Hi, you hear me?
Yes.
Okay, this is our manager, Swiggy Lab Amsterdam. So my question, my question is about something that I like to call it the ramification problem or implication. So of course, most of the stuff we've seen here are very interesting, but mostly is on as a classification problem. And especially you mentioned the different stakeholders might not agree on what is fair with some particular solution. So when you have not just only like a classification problem, but like when a policymaker wants to implement some decision, right? Maybe let's assume that it's also simulated somewhere before taking the decision. So consider, okay, maybe I should give an example. It's much easier. Let's say there is some certain groups that we want to make their life or whatever the setting much more fair by implementing some sort of policy. And these people also agree. It can be a tax reduction for an immigrant community who apply for a mortgage or something. But when you make this policy, it could be quite the case that, you know, there are some maybe 100,000 people who you approve it for one, maybe you need to approve it for everybody. But then it just makes the house prices even higher. So you are left with not too much change, right? And this is the case when even the different stakeholders agree on the fair of this kind of advantage. So my question is then, do you know of any framework or what is your view on it? If there isn't any, so it seems to me that such framework needs both the causality, right? When we do this, what would happen? Plus the maybe multi-agent perspective or the game theory perspective, and everybody chooses. So a big majority chooses this, what would happen, and that kind of things.
Excellent question. So I'm aware of a couple of lines of work that think about this issue. Indeed, the vast majority of work in the field is not just classification, but really binary classification. So it's very narrow. I think more and more there are extensions to many other settings, but still, I think, way overrepresented by binary classification. That said, so thinking about policy and sort of impact, maybe downstream impact, which I think is your question was about. So one, there was a slide I put up a few slides ago on delayed impact, which thinks about the question. They mostly are pointing out the problem. So they're saying, it's exactly what you said, that well-meaning fairness interventions actually could be worse downstream, both if you think just purely decision-making, but even say resource allocation or other things down the road. So different policy sort of downstream implications. We're suggesting that we need tools that think about the entire pipeline or entire system post-deployment, not just the sort of straight, say, predictive learning piece. There's a little bit of work, the one I'm thinking of right now, I don't have a reference in hand, but by Kussner et al. That thinks about causality and sort of causality within pipelines and sort of downstream effects, and thinking about building fairness measures, not just at prediction, but actually sort of post-intervention. So there's a bit of work in the field about this from that point of view. There's a little bit of work that thinks about, say, using things like reinforcement learning type approaches. Right. So you can, again, interventional, but interventional with the RL view. So you don't have to deal with trying to estimate causal structure or causality from observational data. Those are the two main lines of work that I'm aware of. So a little bit of work pointing out the problem you've noted. Indeed, I think that's a serious issue. Downstream effects matter. And then a bit of work trying to investigate solutions.
Thank you very much. Would you, when you share the slides, would you put these works on the?
Sure. Yeah. Probably need a reminder, but I'll put a note now to myself to do that.
Thank you very much.
Okay, so we'll go to conclusions and then maybe open the floor for last questions. So I guess maybe a through line in our discussion today is, again, as maybe many of you might easily agree, fairness is a nuanced and challenging issue, lots of open questions, thinking about user agency, metrics, impacts, have unknown and broader impacts. So again, tied to the previous question. Expectations and notions of fairness are unlikely to be static. I think I like the way Olga put it at the beginning. It's currently June 2022. Some of this could change, I think, very easily between now and whenever you're watching this. And so I think one good way of hopefully attacking the problem is to come up with tools that can evolve as society evolves and society changes. There's, I think, a really nice argument for documentation and software engineering practices. So in addition to what Olga mentioned, pointing to Gabriel Dahl's work on data sheets, there's a really nice talk, keynote in 2020 by Charles Isbell, talking about software engineering practices and the impact they could have on better machine learning, specifically thinking about algorithmic fairness in many instances. I think is a good place to look for sort of changes to the enterprise that could make a positive difference. I think some common threads in the tutorial so far, we've talked about the socio-technical nature of fairness. Algorithmic contributions, again, don't go end to end, so should be appreciated in that way. However, they can provide useful tools, they can provide perspective and context, and so I think are good contributions, but again, to fully have impact, often need to be connected with real use cases and real impacts and real harms. We've tried to avoid oversimplifying. I think the bottom line is it's a complex problem. I think it's best to accept and deal with it that way, as opposed to trying to force it into a smaller box. And there may not be simple solutions for all cases, and maybe that's fine, because I think the cases that we can understand and can solve, we can make hopefully positive difference on by studying. Okay, so there are a few other narratives we didn't talk about, but I want to throw up here, maybe just mention briefly. And then we'll summarize and leave open for final questions. So one narrative we didn't talk about, there is, I think, a lot of interest in thinking about the effect, the extent to which representation and the people who build the tools matters in better systems. Because whoever builds the tools often decide what applications to work on, where to collect data, which solutions to explore, how to evaluate, and see all this through their lens, individual lens, and often demographic lens. And so it can matter in many cases. And if we're aiming to build systems that benefit everyone, I think Olga and I would agree that better representation in the tool builders can have a positive impact. Also, there's some literature that suggests strongly, I'll let you read this at your leisure, that a diversity in teams also leads to more diverse solutions. Other narratives is, to what extent is fairness your responsibility versus someone else's? I think this is can be a challenging question. So conversations about fairness can be hard. I think they can sometimes be emotionally vulnerable or emotionally charged, depending on the setting, or defensive. And I think as in response, there is some history of different stakeholders punting the issue, thinking someone else will address or solve the problem. So practitioners might think about this as this is purely ethics and outside expertise or interest. Companies, for privacy reasons or IP reasons, may not want to open up the algorithms that they're building, which makes auditing for various issues challenging. Stakeholders external to practitioners, so individuals, ethicists, lawyers, policymakers, and so forth, may not have the training or agency to directly address or fix issues without partnering potentially with folks in this room. And so the worst case outcome of this, and I think this is happening less and less, so this is probably a good thing, but the worst case version is that everyone punts and nothing happens, which can lead to just worse harms for all involved. I think it's mentioning explicitly that this is something that's worth thinking about if you're working in this area, in our areas broadly of interest. Okay, so concluding the tutorial today, thank you for your patience and interest. We've covered a variety of what we hope are interesting common narratives. We've intentionally tried to highlight a lot of the nuance. So we've talked about narratives, including one, that fairness issues only come up when working with people or people-related recognition. The right answer is to define a metric. Everything else becomes trivial. Bias in data sets is inevitable. We need to learn to live with it. Problems of data sets are getting either better or worse. The problem can be solved at the feature level. Fairness is a training data set problem. And or your favorite algorithmic framework solves fairness. With that, we'll maybe open the floor for additional questions. If you agree, you disagree, if you have any subtleties that you think we missed beyond the questions asked already. Are there other narratives that you think are useful or maybe common that are useful to think about and may not be covered in any of what we've talked about so far? So I'll open it up for final questions or comments.
So I first have a very specific question. I wanted to understand better what the limitations of the causal approach were. I also want to thank you both actually for excellent coverage of this topic. And I also see a certain subtext here of themes from philosophy. Like when I see this, I kind of hear Rawls in my mind as you're describing all this. There is subtext from sociology, subtext from psychology in terms of telling Olga about things like face validity or ecological validity and so forth. So there are all those themes, I mean, that are pretty much there, I think, that are kind of, I mean, they need to be juxtaposed with all this in some manner. I don't exactly know how. But anyhow, I said a mouthful and I'll let you respond.
Yeah, thank you. That's an excellent set of questions. I'll discuss some and Olga, feel free to jump in. So I think a lot of what we discussed is either directly or indirectly related to classic philosophical notions. We didn't cover them in detail, partially on purpose. I think we wanted something accessible to a typical CVPR audience member. And so they're phrased in these terms. But indeed, I think there are connections to broader notions and philosophy and psychology, and just measurements and statistics as well. Your comments, thanks for the kind comments on the tutorial broadly. To your comments about causal, I think the main challenge is not that special to fairness. I think it's a challenge with causality broadly, which is while in cases where you know the causal graph, I think causal frameworks are very, very powerful because they do get at something really closely related to intervening in the world and interventional outcomes, which pure correlational approaches can often miss. So that aspect of agency in the world in causal approaches, I think, is maybe some of the strongest components of it. However, causal approaches to be effective do require this causal graph knowledge. And the causal graph knowledge often requires sort of untestable set of assumptions. So there's a very strong limit to, if I give you a set of causal graphs, and say a data set, you're quite limited in the ability to tell which of a set of causal graphs generated a certain data set if you're going to use observational techniques completely. And the reason is that purely for observational data, lots and lots of causal graphs are valid are valid generative models. And so you can't discriminate purely on observational data. And so you're left with relying on expert knowledge and maybe, or explicit interventional experiments. So what this means is that you can't rely only on observational data in order to tell apart different causal graphs. And so in algorithmic settings where we try to do, particularly in sort of modern causal approaches for learning, I think a lot of the effort is in causal approaches using observational data alone. And so there's a gap there that has to be filled by experts and requires strong dependence on believing an expert description of a graph. And we know that that description is vulnerable, meaning if it's wrong, it can be impossible to tell based on data without doing randomized experiments, essentially.
Sammy, there was a big thank you to you. That was a very thorough answer.
Oh, thank you. It's a great question.
I think we may actually be able to. I feel like if we pop out this microphone, then it might be easier. At least like rotate it.
Should I come down?
Yeah. Then the camera will catch you.
Okay. Can you hear me?
Yes.
Okay. Yeah. So I guess I have a question on your last suggested narrative. In terms of I guess motivating other stakeholders or perhaps stakeholders like us who are the practitioners or the model developers or builders to care about fairness and I guess solving the problems in at least the ways we know how to. Do you have any thoughts on how we can kind of, I guess, convince others to care or kind of identify tractable perverse incentives that we can kind of change or move in a direction that gets people to consider these problems when maybe they don't normally?
Yeah, that's an excellent question. I think a fun, challenging one. Another one, if I'll go to jump in, you should. So there's a really nice discussion. The paper I'm thinking of is by Hannah Wallach and colleagues, thinking about fairness and its intersection with practitioners, that I think talks about some of these issues, including implications and the ability to sort of get colleagues to care about these questions when building real systems. Some of what we've tried to do partially is to say, I guess for folks who just care about algorithmic questions purely, there are still interesting questions to think about here and answer part of the question, though not everything. I think for trying to advocate, say, within a company or something, I think there's some practical reasons that it's maybe easy to motivate caring. I think the legal guidelines, there are, I guess, media bad outcomes, like cases Olga mentioned at the beginning that many companies are sensitive to, and even in the most I guess the worst reading of, say, what people might care about, they would typically often care about bad media outcomes. And so that might often be sort of a reason why people would take some of these issues seriously. I guess we hope that there are broader views on equity that drive people to think about these questions. But I think, I guess I'm not so naive to think that all of my colleagues will feel the same way. So I guess beyond the practical, the explicit, say, legal and media reasons, and some of the, I can't remember offhand, but some of the, I think, nice discussion in the paper I mentioned. Let me think some more. I'll punt a little bit. Think of other good arguments in real time.
Yeah, I'm happy to say. So I think there's a couple of ways. One is I think that Sammy sort of covered, of like, you can pitch a particular particular if you're talking to, you know, a company, like, right, here's a legal concern that you might face. I think generally speaking, a lot of the time I'll try to connect with sort of what is the person's driving goal, and try to kind of think about it. So this is part of why I think it's very helpful to have all of this like literature at your fingertips, such that you can pitch it at the level at which so the person cares about kind of accuracy on a particular task. You can explain, well, right, so your task is actually suffering because you're not considering these like fairness along this dimension, or you're not considering sort of this subtlety of that, and sort of try to connect it, even if they are resistant to the idea of fairness, but you know, try to the extent possible to show, oh, you know, there was this paper that showed that like accuracy can actually improve as a result of considering fairness. This is also particularly true for me. So I talk a lot about representation and diversity of people, diversity of thought, and sort of being inclusive as a community. And they're also frequently, I will get pushed back on that, of sort of, why do we need that? We're just trying to have a, you know, we're just trying to do computer vision. We don't need diversity. And I've heard this before. And so the counter to this, again, it's helpful to have the papers that say, well, okay, sure, you don't want to care about inclusion and diversity. Okay, I will sort of hold my nose for a second here. But there is research that shows that more diverse teams lead to more creative solutions. Like, you actually have a better research community, you find better solutions, you do better research if you have more diverse teams. That I've actually had people kind of respond to that positively, even if they don't believe the arguments that I think they should believe about the ethical side of this. And I think the last bit is there's a lot of opportunity to sort of lower barrier to entry here for people who, so like a lot of the work that we do is around kind of building tools to enable people to do the right thing. So a lot of the time it's not the resistance to the idea of fairness, it's sort of like the cluelessness almost of like, well, it's too complicated, I don't know where to get started. And so I sort of know my standard thing of, you know, end-to-end training with the labeled data set, and I'm just going to do that, I'm not going to care. And so the trick is to try to build tools or interventions or metrics, and sort of release the code, put it out in the wild, and make it easier to do the right thing without even, you know, having the bandwidth to sort of fully engage with it. So that's the you know, some extra things to maybe keep in mind.
Yeah, that's excellent. I found the paper. I'll add it to slide update before we share it. The one I was thinking of. It's assessing the fairness of AI systems, AI practitioners, processes, challenges, and needs for support, which explicitly talks about sort of some other strategies for thinking about engaging with others and thinking about these questions. It's an excellent question. Thank you for asking.
Thank you.
Right. So I think we're almost on time, actually.
Yeah, looks like it.
Okay.
Thanks, everyone. It's wish could be there in person, but I don't know. Hopefully next time. It's great.